We will now see the electric field and electric charge inside a conductor, which means that inside a metal or any other conducting material. So we see there are four things that we need to see here. One is that the electric field inside the conductor is zero. The charge on a conductor will be on its outer surface or on the surface. The electric field outside the conductor is perpendicular to the surface, and the charge density on the surface is, all the charge is on the surface, its density or the amount of charge is greatest where the radius of curvature of the surface is smallest, and the electric field is also the largest over there. So let's look at each of these in a little bit detail. So let's look at the first one, that the electric field inside a conductor is zero. So if we have an electric field that is, let's say, uniform, and it's from, let's say, left to right, and we have a conductor over here, so that's our conductor. So as soon as this electric field is switched on, then because the electric field is going from left to right, then the electrons in here, which are free electrons and they can move, so they will be attracted towards the left, and they will move to the left, and they will start collecting on the left face, and the other face will start becoming positively charged. So we will have electrons collecting on the left side, so this becomes negative, this becomes positive, and because of this charge there will be an internal electric field from positive to negative. So now there's an electric field due to the external field, which is to the right, and there's a field inside due to these charges to the left. Now if this field is bigger than this field, the net field is still to the right, and more electrons will come to the left, until this field becomes exactly equal to this field, and so the sum of the two will become exactly zero. At that point, no further electrons will come over here. So the result is that because the electrons come here, they create a field that's opposite to the external field. Enough electrons will come that the resultant field becomes exactly zero. Now this takes some time, but that time is extremely small. It's about 10 to the power minus 16th of a second. So it's essentially an instantaneous process. So as soon as you put the metal in the electric field, the electrons will immediately come to the left. This will become positive. Electric field inside will become zero. Now this is true whether it's a solid metal, a solid conductor, or if it is hollow. Even if it's hollow, there's an air gap inside, or an air bubble, or it's some metallic container with only a shell, but inside it's empty, the electric field will still be zero inside it. Now the second is that charge resides on the surface. So let's go to Gauss's law, and let's suppose that we have a conductor, and we give it some charge. So we take some rubber, a rod, and we rub it on silk, and we touch it to it so that it gets an excess of electrons, or you can charge it any other way. So the electrons will come in here, the extra electrons make the whole thing negative, but if these are the electrons, they will push each other apart, and they will all collect as far away from each other as possible, which means that the charge will come and collect on the surface, and there will be no charge left inside. We can also see this by Gauss's law. So suppose this is our conductor. We make a Gaussian surface, and then we look at the flux that is leaving this Gaussian surface, and that flux we know is the E dot A, which is the electric field E, and that's the area. So that is equal to Q in over epsilon naught by Gauss's law. Now, because the electric field is zero, the flux is zero, and if you put the flux equal to zero, that means the Q inside is zero. So Q in here is zero. Now we can move this Gaussian surface all the way to the surface, right to the edge of this material, and then there'll be Q in will remain zero inside it. So that shows that the charge will be outside a Gaussian surface that's just inside the surface. So that's the second thing, that the charge will reside on the surface. Now, what is the nature of the electric field? Number 3, the electric field just outside is perpendicular to the surface and is equal to the surface charge density divided by epsilon naught. So we can make, in this case, a cylindrical surface here, could be going inside like what we did earlier. So the surface charge density here is sigma, and we will have an electric field going out here, but there is no electric field over here. Only field is on the outside. What we did earlier, where we had a plain sheet of charge, and we took a cylindrical surface, then electric field in that case was going out from both sides. But in this case, there's no electric field here, so it's only here, and that results in the electric field being equal to sigma over epsilon naught. And of course, the electric field has to be perpendicular to the surface at every point, because if it's not perpendicular to the surface, for one thing, it could intersect, and for another, if it is like this, there'll be a perpendicular component and a parallel component, and that parallel component will cause the charges to start moving in this direction, and they will move until they become enough on the other side so that the electric field becomes zero. Now, because the electric field is always pointing outwards, so this is the surface. So if we take the delta V as the integral of E dot ds, and E is this way and ds is this way, so we're doing the delta V from a point here to here, or the delta V between 2 points on the surface. So the E is outwards and delta S is parallel to the surface, which means that E is perpendicular to ds, and the dot product would be simply E ds cosine of 90, which is 0, and so this term will become 0, which means that the delta V on any 2 points close to each other on the surface, the delta V will be 0, which means that if delta V is 0, it means the V is constant or same all over the surface. Well, if the voltage is same all over the surface, what about the potential inside? Well, we know that the electric field is dV over dx, and the electric field inside is 0. That means dV by dx is 0. So if that's our x-axis and we want to go inside, so dV by dx being 0 means there's no change in the potential. So that implies that the potential is the same everywhere inside the solid. Inside a conductor. Now this applies only for a conductor and not for an insulator. All of these others also applied only for a conductor. So the potential is same everywhere inside a conductor, and it's equal to its value on the surface. So whatever is the value of the potential on the surface, that is the same everywhere inside. We will now look at the fourth condition, that the electric field and the surface charge densities are largest where the surface, the radius of curvature of the surface is the smallest. So where we have sharp points, radius of curvature is smallest. So if we have a surface that's somehow pointed at one end, then the charge density in this area will be the largest, and the electric field coming out from here will also be the greatest. So let's show that. So if you have a sphere of radius, a larger radius, let's say r1, and another sphere which is somewhat far away from it of a smaller radius r2, and we charge this and we charge this and we connect them with a wire. Now if we do that, then the whole thing becomes essentially one object, and so the potential will be the same over it. Now the electric field just outside it would be E1, the electric field just here would be E2, and we can say that E1 is KQ over R1 square, that's just on the surface, and E2 is KQ over R2 square. Well, Q and Q may be different, so that's Q1, it's Q2, Q2 and Q1. Now we know that the potential for 1 is going to be KQ over R1, the potential on the surface, and the potential on the surface for number 2 is going to be KQ2 over R2. And so we can write the E1 as KQ over R1 and another R1. So that's going to be a V1 over R1, and E2 can be written as KQ2 over R2 and R2. One of them becomes a V2, and we have the other R2. So we can now rearrange that and say V1 equals E1 R1 and V2 equals E2 R2. But because they are connected together, so V1 equals V2, and therefore E1 R1 equals E2 R2. Now R1 is bigger than R2, therefore E1 must be smaller than E2. It's because the product has to remain the same. So if R2 gets smaller, E2 has to get bigger. So this means that E2 is greater than E1. So the smaller radius sphere has a greater electric field. And so the smaller the radius gets, the bigger the electric field gets. And ultimately, if we consider a non-spherical surface having a point, then at that point here, the radius of curvature is very, very small. And so the electric field here will be very, very high. And if you add enough charge over here so that there's going to be a spark, then the spark will take place over here. Now lastly, we'll look at a Faraday cage. So if there is a metal container, for example an aeroplane, which is a metal shell, and people are inside it, and this is a metallic shell, so the electric field inside is going to be 0. So even if lightning hits it, then nothing will happen to the people inside because they are inside a metallic object, and so the electric field inside is 0. Similarly, if you're in a car and lightning hits the car, well, the engine may turn off, but the people inside would remain okay because they're inside a metal cage. So devices like this are called Faraday cage, and it does not have to be a solid continuous shell. It could be made of a wire mesh. So if you have some kind of a box made of wires, and the person is inside it, and it's a wire mesh on all sides, top, bottom, and all six sides, then you may have huge sparks hitting this, and the person inside will be okay, will have no effect, even if that person touches the inside of these wires. And that's because the electric field inside or on the inside of each of these wires is also zero.